Welcome to the pre-recording of lecture 23 of computational geometry. In this lecture, we introduce arrangements of lines very slowly, starting with a problem coming from computer graphics. Although by the end, we will actually forget about computer graphics. We will see this merely and mainly in pure geometric terms. So we have a problem of counting points. We will transform this via duality into counting lines. So that's actually the main story of this lecture. Duality. Okay, points become lines, lines become points. So let me um, go ahead with this. So what is the problem in computer graphics? So computer graphics applies a technique called ray tracing, determining the visible object at each pixel. So what ray tracing really is not so much of a concern to us, but what we consider here is a sequence of pixels, and we have the objects that are being represented at the right of the red line. So we have a 4 by 4 grid of pixels that we here consider. We have the boxes that are where the center is at the right of the red line. Those are entirely shaded in green. The other ones are staying white. So a pixel is this not a dot, but it's actually a small square area. Now here it is represented as being lighted or not, so it's pure binary whether you are at the right of the red line or not. So if you do this, then actually your picture will actually not look very good. If you want to really, if the red line is really the edge, then it will appear jagged. So what can we do with this? We can actually change the intensity. So here we have white and green. You can have all shades of green, depending on how much of the small square area is actually to the right of this red line. Okay, so let's turn this into a mathematical problem now. Perhaps I should first point you to the picture here. After all, this is a course in geometry. We look at pictures. So we have a unit square. We have dots in there, and we have a red line, and we look at the area now below the red line. If you have taken a course in calculus, then you will recognize that we are computing the area under a line between 0 and 1 here. Now, for the sake of this, the unit box, we actually chop off a quarter, so the area is 1 over 4. One way to compute or to estimate, to approximate integrals or areas is by sampling. So we have 3 dots that are below the red line out of a total of 10. So we have a sample set that is 10. So our approximation is 3 out of 10, which is not 1 of 4, but the error is 1 over 20. So 10 samples is actually not that much. 1 over 20 is already 1 magnitude less than the actual value. So thinking with decimals, 0.25 is 1 over 4. The error is actually 0.05. so not bad. Okay, so let's read the definition now. The definition defines the discrepancy of a sample set. So we have the unit square, we have a set of points, and then we have the half plane. Here we are going to work with below, but the half plane actually determines what is visible or not. So we have the area, so that is what is exact. And then we have the fraction of the sample points in the visible area. So that is this mu of S. The mu of H doesn't depend on the sample points. So that's the area that you see shaded in green here in the picture. The approximation actually depends on the portion of the sample points that actually lies in the half plane that cuts out this triangle here in the picture of the unit square. And then the discrepancy of the hyperplane, of the half plane, sorry, of the half plane with respect to the sample set is defined as the absolute value of the difference between the exact area and the estimated area, just by counting the number of points below the red line here or inside the half plane and the unit square. Okay, so this is discrepancy. And why does this really matters? We want to know this area because this determines the intensity. So if you want to, if this unit square U represents a small pixel square, then we want to decide how to light this up. So with the exact area, it is 25%. With the approximated area, it's 30%. So that's the last thing I probably will say about computer graphics. Okay, so there is the half plane discrepancy, a new definition here. You can see that if you look at the pictures, again, look at the pictures first. If we move the half plane, if we move this red line up, we actually are increasing the value below. We're increasing the green shaded area. But you see that as we do this gradually up to this dot here, of all the lines below this red line here at the right, there are only 3 dots below. So actually, the more we push this red line, the more the discrepancy actually increases. The discrepancy indeed, again, the difference between the area, so the area, the shaded area increases, but actually the sample, what we sample here, the ratio does stay the same because we keep the same dots. So the question is, what is actually the half plane discrepancy? So in some sense, what is actually the largest error we can make with the sample set? That's what is the half plane discrepancy. So I mentioned on the previous slide the error was 0.05, which is actually quite good if you are estimating 1/4. But how bad can it actually get? So this is what we are now going to try to compute. This is called the half plane discrepancy. So it's the supremum of all the discrepancy of the set of all half planes that we can consider. So, okay, so the main observation, or the observation that I made it already, that if you shift the the half plane, as long as you don't shift the sample estimate, then actually the discrepancy only decreases. So if we want to maximize this half-plane discrepancy, it's a supremum, so it's not a finite set. There's no maximum. Excuse me. If we are doing this, then actually the point is here, and the main point is that there should be at least one point on the boundary of this half plane. Because we cannot have a supremum if there is no point, then we can always shift a little bit up or down. So it depends on what we consider. If the half plane is up, then we decrease it, and we actually are increasing. So we are not at an optimum. So if we look below, then we just increases up. So that's actually the whole point here, and perhaps I should underline this. So what is the point of this slide? So it is over here. So the boundary of H of this half plane must contain at least one point of the sample set. Okay, natural question. This half plane is actually determined uniquely by 2 points. Can we have maximal discrepancy with only 1 point? That's the question that we are now asking. All right, can that happen? So here you see, now we are looking at the area above. Doesn't really matter. So we have a yellow shaded region. So we look at all the lines through this point. So in some sense we can shift up to a point, but then we can still wiggle the line. Should we actually wiggle till we have another point, or in which direction should we wiggle? Now wiggle, rotate around an angle. So we can, if we have only one point on the boundary of the half plane, then we can look at a parameterized problem. So we can look at the optimum of all the areas that we can get in function of this angle theta here. So even if we have only one point and this boundary is not really uniquely defined, we can turn it into a problem that has a unique answer. So it is actually the maximizing of the area. And that then also corresponds to the original problem on the half-plane discrepancy. So we want to maximize the difference between the area, here the yellow area, and then the estimates that is by the ratio of the samples that are in the half plane and in the unit square. Okay, it is now a calculus problem. So let me go through this. So we are computing the area of the half plane. So we have the point with coordinates px and py. So we have a rectangle. We have the unit square 0, 1 from 0 to px here. And then we have the upper boundary, which is 1. So we have 1 minus py. So that's why we actually see the term px times 1 minus py. So that's the middle. So the middle term, so this is the area in the yellow region. The middle term is this rectangular box here. So px, first coordinate of the point, and then 1 minus py is this vertical line here. Then we have two triangles. The triangles are determined by this angle. So we have the tangent that is defined by the 1 minus py over the b, so the b that I have defined here. And then we can also work with the a over the p over x. So we have these expressions for the tangent of phi. Um, that is being used to eliminate the A and the B. So we don't know what is the A and the B, but we can express the A and the B in terms of this tangent, or if you like, the slope. It also expresses the slope of the line and the given coordinates of the point Px and Py. So this leads us then to these two areas. So we have here you see A is Px times the tangent. So Px times the tangent times half of Px. Why half? Because otherwise we would have a rectangle. So this is the area of this triangle. We do the same thing for the other triangle, eliminating the b, and then we have the height 1 minus py, and we take again half because we have a triangle. So this gives us then this nice expression in terms of the coordinates of the point and the slope of the line. Good. Compute this now. Well, it is a calculus problem. So we compute the angle of the maximum, and that gives us the expression of the discrepancy. So we have a continuous formula evolving depending on this parameter, um, the angle, and then also the subscript here. So in some sense, if you would see this as a function, it's a function of three parameters. But in mathematics, we like subscripts. So the point P is the subscript of this function H. Okay, so the subscript, so both the um, so the point being here actually that the area will change if the angle changes. Also, actually, this count may also change. So we have to determine the angle where the maximum is obtained. We can swivel around. Now, of course, there are some discrete points. So there are the corner points at the box that we have to keep into mind. So remember, calculus, if you do constraint optimization, you look for the critical points, but also don't forget the bounds of your interval. Same thing happens also here. Okay. First exercise is actually to plot this. So how would you do this? Well, we work with the unit um, square. Generate 2 points at random and graph the function for some angles. So you can also pick a random angle. And it might be good to actually also plot matplotlib again, could be nice. Plot the line, or well, shouldn't be matplotlib. You can make two plots, so you have the shape of the angle, and then you could, for certain parts, also plot. So you can discretize this for several angles at the other side. You could see how the line evolves. So the point of this exercise being that it gives you kind of a feeling of what we are doing here. In this slides, it could have been an extra illustration of the problem. Okay, what are the problems now? So these are the two problems. So in some sense, the exercises are meant for us to pause a little bit. And I should pause a little bit. So I am 20 minutes in this lecture and have already gone through half of the slides. Okay. Here comes now the first result. So we have the extrema. We will hit the vertices. And why 8 times? We only have 4 corners, but you may each time you may hit the corner, so assuming that our point is smack at the center, you can or not smack at the center, otherwise it's too symmetric, but sometimes you hit a vertex at the right, or sometimes you hit a vertex at the left. So in some sense this is obvious if you ever had tried to move, say, an object around the room, you may hit the object may hit one wall and may hit another wall. So the four corners can be hit by one side of the line and by the other side of the line. So this is why you have 8. Okay, we have 2 points, and n is the number of sample points. So we would like to know what is the cost of computing the discrepancy in terms of the number of sample points. Why is that useful? I mentioned estimating of definite integrals. Can you actually, in these number of points that tend to grow, can you actually determine the error or the maximum error? How much time does that take? So it's actually quite nice that here the first lemma is that if there's only one point on its boundary, then actually you can do this in linear time. So if there are two or more points on the boundary, then it takes longer. So this is kind of an interesting result. So if there is one point on the half plane on the boundary, then we can solve this problem in linear time, linear in the number of sample points. That's a nice result. But now we have to find the number of the first type of candidates. So I'm actually now a little bit confused because there is a lemma and then there is the last line. So there is a straightforward way to do this, and that is n square time. So it is here the straightforward that shouldn't confuse you. So the straightforward way would be a double loop in the number of points. So you consider each other point, and then with each point also all the other points. So that's the straightforward way of looking. Duality. So I'm at the half of this point, of the half of the lecture. I will try to explain how we can transform this problem, or looking at the original problem of counting points into counting lines. So in some sense, it looks a bit far-fetched, but we are starting a lecture on a chapter on arrangements of lines. So it will be a motivating problem to look at line arrangements. Okay, lines can become points and points can become lines. Again, look at this picture here. We have two lines and 2 points. So P1 and P2 are transformed into 2 lines. At the intersection of these 2 lines, red lines, is the dual of the line which is spanned by the 2 points. So this is very beautiful. So I worked it out with the coordinates. So we have P1 and P2. P2 has coordinates 1, 1. So this corresponds then to the line minus x plus, I'm sorry. So we have here P2, P star 2 is y equals x minus 1. You see here the formula, 1, 1. So it's 1, 1. So the dual of the point is the line. So the dual of that other point, um, so let's now take again minus 1. So we have minus x plus 1. Now, what are the duals of the lines? We read this actually backwards. So we have lines with slope and intercept. Don't think about vertical lines at this point. Um, so we have lines and an intercept. Sorry, we have lines defined by a slope m and an intercept b, also two numbers. With that, we correspond the number, the point, with coordinates m and minus p. So you can therefore see that this line here, the line is y equals x, so no slope. So that's why there is no height in the coordinates of this dual of this line. Okay, so you can read this picture from left to right, but you can also read it from right to left. So this will be the next observation. So here are the observations on the duality, the same picture again. So saying that you can read the picture from right to left means that the dual of the dual is the primal, or the dual of the dual is the original. You can verify this, but actually the second exercise is to prove this. If you prove this, well, you have to change the notations a little bit. So you have a line, and that will give you the original points back. You have a line, and that will give you, you have a point, and that will give you the line. So it's just as simple as writing it down, following the definition. But now you actually apply the definition in the opposite way. So here we started with a point with coordinate px, py. You start with a point with coordinates slope and minus the intercept. And then you see that actually, hey, you do have a line with intercept m and slope b. That's all there is to it. So for the incidence preserving, so if a point is on a line, then the dual of the line lies on the dual of the point. So what does it mean to stay on a line? Well, here again, don't think about vertical lines yet. So here again, you check if a point is on a line, you can compute its y coordinates from the formula. Slope times x plus intercept. See if you can do this also here. Notice that there is an if and only if. So if you have to prove this, you have to prove both ways. If there's a point on the line, then the dual of the line belongs to the point. If you read it from right to left, if the dual of the line lies on the dual on the point, then actually that means that the original point lies on the line. So there are two things that you need to prove here. The last property is actually the most important one. So I stole this exercise from the textbook. The exercise from the textbook asks mainly about the order preserving property, because in some sense that's the crux. That's actually what binds the first part, the computation of the half-plane discrepancy, with the dual problem. So if a point is above a line, then the dual of the line is above the point. So you see, we can translate actually the problem of points in a half plane to counting lines, or counting, I'm sorry, counting points. Um, we will count lines. I will try to explain this in a minute. But again, so let me not rush ahead here or extrapolate too much. If you solve this exercise, so the first two parts are reading the definition in another notation, essentially. this is reflecting on the definitions, but then more in an algebraic way without looking at the pictures too much. If you prove order preserving, you should again, so this is an if and only if, so you should prove both directions. So you have the if the point is above the line, then the dual of the line is also above. You can actually verify this here. Here actually we have a point P1 that is below L2. So we see here that the dual of L2 is actually below the dual of P1. Okay, so I was have to finish this. So if you can also read this from right to left. So in some sense you could make it a little bit easier. So if it is order preserving, if you can prove the order preserving in one way, then actually you can say, hey, I have already proven that the dual of the dual is the original. So that also makes that a little bit easier. Okay, fine then. So I'm half hour in. Um, let's talk a little bit more about duality. What is the dual of a line segment? So we considered early on in the course the line segment intersection problem. So line segments, they become double wedges. Very interesting. So what is a line segment? It contains all the points that are convex combinations of the 2 points. It's kind of you have these 2 points P1 and P2, and you kind of try to mix them. So here you could also say we have 1, 1, we go to 0, 0. So we divide 1, 1 by positive constants, and we keep on actually, we do this in the opposite way when we start with P1. So it's kind of a mixture. What it means on the right is actually that you let this line Q star, you let it actually slide. So you have a range for its slope. So it's a double wedge. We have a left part of the wedge and a right part of the wedge. So what is at the center here is this most likely the getting a little bit confused now again. So the point 0, 0 has kind of a strange dual. So 0, 0 actually corresponds to also the line y equals 0. So it's actually the entire x-axis. But you should actually, so yes, okay, very fine then. So it's actually wrong to look at the single point. So the point 0, 0 here becomes to the y-axis. So this is when the Q star is entirely flat. Okay, yes. Okay, we understand duality, do we? What about parabolas? So we talked about parabolas a lot when we talked about the Voronoi diagrams and the beach line. So here is another way to look at parabolas. So what is the dual of a parabola now? This is the exercise, but the slide will get you started to think about this problem. So you look at a point on the parabola. So the parabola is here a very simple one, x squared divided by 2. So actually, if you have a point, you actually have a line, the dual of a line. Okay, so what happens now, every point on the line, on that parabola becomes a line. So actually what you have, if you let this point slide along here, you actually have all kinds of lines that are tangent to the point on the parabola. That's kind of nice. So um, so that's actually a nice property. Um, so I have to think about this also a little bit, why that is, why that line is tangent to the parabola at the point. So um, so these are points that actually are satisfying this equation here. Perhaps it can be an accident. So I'm actually extrapolating from this. So for this particular point, the line turns out to be a tangent line, but you can kind of see, and here is how you can see it. Purely formally, the dual of the point is here explained. So the slope of the dual is the first x coordinate, and the intercept is this p squared divided by x over 2. And there you now see it. So if x equals the so we have already here the function value that comes in. If you so what I was trying to get at is that this line actually passes through the point. It is the tangent line because if you take the derivative, actually you have y equals x. So it's not always the case. So it depends on the very particular coordinates. But the slope is actually always, in some sense, if you plug in the x coordinate, it's actually x squared divided by 2. So it's actually not always going to be the tangent line. Again, I'm rambling over this, trying to reason about this. Uh, the programmer's way to do this would be to make a plot, do this for many, many points, and make the plot. Draw, you can also do this by hand, of course. Okay. All right, so we are actually arrived at the last and final part. I'm almost 40 minutes in and don't want to stretch this too much longer. We had the counting of the points below a line. Then this gets translated in the number of lines below a point. This is a different problem. And that's the problem that we are going to solve with arrangements of lines. So arrangements of lines occur in many other areas. So even if we actually forgot about computer graphics by now. But if we are still thinking about computer graphics, that is a translation of the original problem. This problem, counting lines below a point, can actually be solved differently than the original problem. What's the intuition here? Why could this now be easier? Well, we're looking for points, tiny points below a line, and that seems to be kind of easier to look for lines below a point. So in a way, you can also again imagine a horizontal line through the height of the dual of that line, and then you simply count the number of lines. So lines are bigger objects, better to see. So that's kind of where the intuition lies. Okay, so vertical lines have to be handled separately, and that can be done in square time. For general lines, we will consider arrangements of lines. So it's important here that we will arrive at the linear complexity. So to kind of give the direction where we are going. So we are proving at the end of the chapter the zone theorem, which is an important property of the complexity of arrangements of lines. If you have a set of arrangements of line, you intersect it with a line, how many zones are affected in the subdivision? It will turn out that this is linear. Um, that is a linear amount in the set of lines that are determined so it's not quadratic. But in the meantime, we have to before we get to the zone theorem, we will have to define what is the subdivision that is defined by the set of lines. So we will define an incremental algorithm for this. And that will be the topic of the next lecture. So in some sense, this is a warm-up. We addressed earlier in the course the polarity of a convex polygon. I then said that this is also the dual of a polygon, but I hope that now it is clear that actually duality is different from polarity. So what we actually considered in the previous lecture, I think it was in when we discussed linear programming, um, long time ago now, we introduced polarity. Polarity is different from duality. So in this lecture, we saw that the dual of a point is a line, the dual of a line is a point. And this is nicely defined, except for vertical lines. Okay. We covered the start of sections of the chapter 8, sections 1 and 2 of chapter 8. Look at the exercises. So the exercises are actually essential for deeper understanding of the concepts that we have covered. I took the exercise 1 of the exercise in the textbook, that is exercise 2 now in this lecture. Arrangements are very important in Seagull. And I had actually time to look at this, but I probably should, well, I can do this. So let me very briefly go into the documentation of Seagull. So if you look into Seagull, you look into the packages, so the overview of the packages, and in the documentation, my internet is a little bit slow. I had not prepared this all that well. So if we are looking at the documentation, which is loading now, I clicked on the arrangements. So the arrangements, so on packages, you see here arrangements is there. If you click on the documentation, so I'm clicking on the documentation, so nothing much is happening because my internet is slow. Then you will see that, oh, here we are. So here we are at the 2D arrangements. I pointed to arrangements earlier in the course because actually here you see arrangements that are determined by line segments, and you see the subdivisions that come with it. We have already covered subdivisions defined by line segments. So these are the trapezoidal maps. But now actually we look at the arrangements of lines. And actually I'm a little bit confused because there are no line arrangements. So you see here the trouble of not preparing this all that well. So line arrangements, in a way, um, they are special cases of line segment arrangements. So I think it should probably be stated like this. Okay, I should probably stop here because I'm starting to improvise too much. So we have essentially already seen the arrangements of line segments when we considered trapezoidal maps. But in a way, if you look at bounding boxes, then every line intersects the bounding box, and we are considering then in that sense uh, the intersection of line segments. Okay, I will stop here. In the next lecture, we will formally define a subdivision defined by a set of lines, and then in the next lecture following, we will prove the zone theorem.